Welcome students for today's lecture on design of tension members. In the previous class we had discussed about what are tension members, what is slenderness ratio, what are the types of section, and what are the failure criteria of the tensile members, and we had discussed about the first point, that is the criteria failure by gross yielding. So just I would like to go through those in a few minutes. So first we learnt about what are tensile members here. Then we just saw types of sections that can be used for tension members. Slenderness ratio is given by lambda is equal to LE by R minimum, where R is nothing but radius of gyration. Effective length is given by LE is equal to 0.85 L. Then I had discussed about what are the limitations for the slenderness ratio. Lambda is maximum of 180 if the loads are other than wind and earthquake, and maximum of 350 if the reversal of load is due to wind or earthquake. Next we discussed about what is the design of tension members. So design of tension member based on the failure criteria of the tensile members. So we have three failure criteria of the tensile members. The first is design strength due to yielding of gross cross section. Second is rupture strength of critical section, and the third is block shear strength of the section. So we have already discussed about the first point, that is design strength due to yield of gross cross section. So today we will discuss about the further two failure criteria, that is rupture strength of critical section and the block shear. So let us see. So in the previous lecture we had already discussed what is the design strength due to yielding, that is gross cross section of the yielding. So it is given on page number 32, clause number 6.1, and the formula goes like this: TDG is equal to AGFY divided by gamma m naught, where this AG is nothing but the gross area of the cross section. Okay. So today we shall proceed with the further two points. So the second failure criteria of the steel is design strength due to rupture of critical section. So let us see in the code book. So this is given in page number 32. So we have here design strength due to the rupture of critical section. So this is for two components, one is for plates and the other one is for the angles. So we have two different formulas, one is for the connection between the plates and one is for the connection between the angle and the plate. So let us see about plate first. So clause number 6.3.1 discusses about the plates, and the design strength due to tension and due to rupture of critical section is denoted by TDN, and the formula is given by 0.9 ANFU divided by gamma m1. So remember, this formula is for plates only. So here in what all we have, so we have 0.9 AN. What do you mean by AN? AN is nothing but net effective area of the member, that is net effective area. What is net effective area? If there are bolted connection, deducting the bolt hole portion, so remaining area in this particular section remains as net area. So that has to be taken into account. Fu is ultimate strength of the material and gamma m1. So this I have written it here. So this is the formula for design strength for plates. TDN is equal to 0.9 ANFU divided by gamma m1. So AN, I told you AN is nothing but net effective area of the member, which is given by. So how to calculate? So there are two components again here, depending upon the bolting system. If the bolting system is chaining, there is a different calculation, and if the bolting is by staggering or diamond pitching with staggered pitches, there is a different formula. So the formula number 1, that is AN is equal to B minus NDH into T. This is for chain bolting, and AN is equal to B minus NDH plus summation of PSI square divided by 4GI into T. This is for staggered pitching. So here B is nothing but the width of the section, N is the number of bolt holes coming in the section, critical section taken into consideration, DH is the diameter of the bolt hole, and T is the thickness of the member. So similarly it is here also. This PSI is nothing but the staggered pitching, and this is the gauge distance. So Fu is ultimate stress of the material, and gamma m1 is nothing but partial factor of safety at ultimate stress for causing the failure. So this can be taken from table number 5. So next is for angles. So the previous formula that was for the plate. So let us see in the code book how it is given. So in code book it is given here. Single angles. For single angles, the rupture strength of an angle connected through one leg is affected by shear lag. The design strength TDN as governed by rupture at net section is given by. So this is the formula given in the code book, wherein you have some component beta. Again, what is beta? They have mentioned it here. And what should be the range? They have mentioned it here. And the most important thing in this formula is, because it is with respect to angles, the most important is calculation of the BS. So that is this value, that is BS, shear lag width. So there are two diagrams given here, 1 and 2. This is for bolted connection and this is for welded connection. So the value of this BS, shear lag width, varies with connection. For bolted it is different, for welded it is different. And here they have already mentioned that the rupture strength of an angle is connected through leg 1 which is affected by the shear lag. So this is the effect that has to be considered. So let us see. So this only I have written it in a proper format, so you can see. So this is the formula how it goes. So the formula is TDN is equal to 0.9 ANC Fu divided by gamma m1 plus beta AGO Fi divided by gamma m naught. This gamma m1 and gamma m naught are the partial factor of safety which you can get from table number 5. Fu is the ultimate stress of the material, Fi is the yield stress of the material. Now the most important is this part, ANC and AGO. What does this C refers to? C refers to connected, O refers to outstanding. What is the meaning of this C and this O? C means connected. Let us take an example of this. This is an angle which is connected to a plate. So there are two legs to the angle. One is this leg, one is the other leg. This leg is connected. So remember A and C. So net area of the connected leg. So this leg is connected. So area of this leg is called as area of net connected leg. Similarly, this is the outstanding leg. Outstanding means what? Which is projected, which is directly not connected to any of the member, which is just remaining outstanding. So such kind of portion is called as outstanding. So this is referring to this AGO. So automatically what happened? This is outstanding and there is no connection present. There is no bolt hole or something. That's why it becomes gross, because the full section is used. However, we already know that AG is nothing but the gross cross section, that is full strength of the section. So remember, ANC is net area of the connected leg. That means this is in this for this connection, and AGO is gross area of the outstanding leg. So it is related with this. So whenever you are solving with angles, remember that you should be knowing which is the connected leg and which is the not connected leg. The connected leg carries out the calculation of ANC and the not connected leg will take into the calculation of AGO, that is called as outstanding. Now, so this formula is explained. Now next we will go to this term, that is beta. What is beta? They have already given here, where beta is 1.4 minus 0.076 into bracket W upon T divided by T into bracket Fi divided by Fu into Bs upon Lc. So I will just like to show you into the code. So if you refer, it is given here, and it has a range, What is that range? It should be greater than 0.7 and it should be less than this formula. Already we have seen what is Fi, what is Fu. We have already seen what is gamma m naught, gamma m1. So let us see in this part, so what are the components. So we have, let us take the first bracket, so W by T, where T is the thickness of the leg, that is, this is the thickness of the leg or this is the thickness of the leg, W. Now what is that W? It varies from types of connection, whether it is bolted or welded. Let us see in the bolted connection. So W is nothing but the outstanding portion of the leg, that is outstand leg width. So remember, in case of welded this is W, in case of bolted this is W. So we got W, we got T. We already know Fi is yield stress of the material, Fu is ultimate stress of the material. Next is Bs upon Lc. Let us see what is Bs. So Bs is nothing but shear lag width. Let us show it here. So Bs is shear lag width as shown in the figure 6. So this is the figure number 6, angle with single leg connections. This is used for calculation of the Bs. Here they are given the formula, Bs is equal to W plus W1 plus T, and Bs is equal to W. Bs is equal to W. Now let us see. So those I have drawn. So this is with respect to bolted, this is with respect to welded. However, when you can see this is the connected leg. So here we have provided a bolt. This is a connected leg. We have provided with the weld connection. So let us see for bolted. So for bolted, Bs is W plus W1 minus T. W we already know, that is the outstand width of the leg. Now W1, this is very important. So W1 is the distance from the edge of the member till the first bolt placed. So this is the bolt center. Here the bolt is already placed. So bolt center. So this distance is called as W, that is bolt hole distance. So W1 minus of T. So this will give for the bolted connection. For welded connection, however, we are not connecting it by producing holes or punching the holes. So obviously full section is there. So it is nothing but Bs is equal to W as it is. That is full width of the section. Next part is LC. Now what is this LC? This is nothing but the distance between the outermost of the bolt. That is distance between the bolt to bolt in the bolted connection. Let us see. This is a bolted connection. For bolted connection, so there are three. This is an example. So I have taken 3 bolts here. So out of 3 bolts, you can see the distance between the outermost bolts, that is outside bolts, center to center, is called as LC in bolted connection. Now what in case of welded connection? Because we don't have bolts here, but we have here welding. So I have taken an example of 2 sides welding. So 1 and 2, L1 and L2. So what is LC for this? It is nothing but the average of the 2. So it will become L1 plus L2 divided by 2. So this is the component. Next, shall we go for the next section, that is design strength due to the block shear. Clause 6.4, page 33 of IS 800 2007. So this is the design strength due to the block shear. They have given the formula. So the block shear strength TDP of the connection shall be taken as smaller of. So they have given 2 formulas. So one is this and the other one is this. So this formula I have written it in the page. So you can see the block shear strength TDB is the smaller of TDB AVG Fy divided by root 3 gamma m naught plus 0.9 ATN Fu divided by gamma m1. Similarly, TDB is equal to 0.9 AVN Fu divided by root 3 gamma m1 plus ATG Fy divided by gamma m naught. So we have here the components. Already we know what is Fy, what is gamma m naught, what is Fu, gamma m1. So we have to understand 4 most important components. One is AVG, one is ATN, the other is AVN, the other is ATG. So what is AVG? So here also again, what is this G and N? I have already explained. G refers to gross, N refers to net. That means wherever G component is there, therein it is related with the non-connected leg, and wherever N is there, that is a reference with respect to the connected leg. What is this V and what is this T? V is representing the component parallel to the load. T is representing to the perpendicular to the load. Let us take an example. So I have taken an example. Let us take first example. This is the angle connected and there are 3 bolting systems. So the force is acting here, tensile force. So it is pulling the angle. So how will it will fail when it is in block shear? So 3 bolts will fail in this portion. You can see this will tear off. So what are the distance? Now this is the load. So parallel to the load is nothing but AVG and the AVN. So let us see. So we have component here LV and LT. So this distance is called as LT and this distance is called as LV. So this only I have drawn it here. So this is the distance LV from this component from the edge till the failure, and this distance is LT. So this is the parallel to the load. You can see the parallel to the application of the load. So in both this we have parallel load to the load LV component, and this is perpendicular. So this is LT here. So this refers to this, that is perpendicular. So remember, wherever parallel is there you will come across V, wherever perpendicular is there you will come across T. So as the case here. So V refers to parallel loading, T refers to the perpendicular loading. When we have 2 rows of bolting, so this is the LT distance and this is the LV distance. So it will fail like this and this will tear off. So this will be LT distance and this will be LV distance. So this is how we have to calculate. So AVG is given by LV into T because it is gross, no deduction. Net means you have to deduct the bolt holes. So LV into T minus the bolt holes. Similarly, gross area of the perpendicular section, so LT into T, net area perpendicular to the load LT into T minus deduction of the bolt holes. This is the process. So this has to be substituted here and we have to check which is the least. We will get 2 answers, one is for this, one is for this. Whichever is least is the answer for the design of block shear strength. Once we get the answer for all the 3, so I will just tell you. So first is due to gross yielding, second is rupture of critical section, and the third is due to TDB. Then the tensile strength can be computed. Tensile strength T is equal to least of TDG, TDN and TDB. So let us show in the code book as well. So here they have clearly mentioned the design strength of the member under axial tension is the lowest of design strength due to yielding of gross section TDG, then rupture strength of critical section TDN and block shear TDB. So it is nothing but list of TDG, TDB and TDN. This is how we find out the tensile strength of the member. So this completes the explanation for the failure criteria, that is 3 failure criteria, that is yielding of gross cross section, then rupture of the critical section and the block shear. So this also gives the formula to calculate the tensile strength. This is how it has to be calculated. So this completes the explanation for the how to calculate and the IS code provisions for calculating the tensile strength of the member. So in the next lecture we shall solve a numerical with respect to angles. So to all my students, stay home, be safe. Thank you one and all.